Okay. Good morning, everybody. All right, so the flus, colds, and no COVID so far are taking hold of this conference in an unexpected way, in that it is two of our invited virtual speakers had to cancel because they're both sick with flus. And that's Olli Führer won't be here at 9 o'clock, and Laura Zanna won't be here after the coffee break. So what we have decided to do is we're going to ask Richard and Sherry, who were the contributed talks before lunch, to speak now. Then we'll have Milan Klöver's invited talk at 9:45. Then we have a coffee break. And then we'll go into breakouts straight after the coffee breaks. So your afternoon breakout session becomes a morning breakout session. We'll have lunch, and then depending on how you're going in your breakout sessions, you can reconvene after lunch or not. It's up to you how you feel, how far you've gotten. In principle, there was another hour to prepare the reports for tomorrow, so you may want to use that hour. And we are canceling the afternoon catering. So at 3:30, there will be no afternoon coffee. So that means you can all leave at your own leisure after lunch, depending how forceful your breakout group chairs are, right? If the two moderators of the breakout groups don't let you go, well, that's for you to negotiate. So basically, the afternoon is a bit at your discretion, right? So work for as long as you want or as little as you want, and then have the afternoon off. We felt that was the better option than finishing the meeting today, which we could also have tried, because there's a few people who deliberately, who are not here today, who will be here tomorrow for the closeout of the meeting and the plenary discussion and the reporting of the breakout groups. Andrew will add something. I just want to remind you, but I don't quite know. I think I will say send any of Andrew, Andreas, myself, Kathy, or Kath your acronym proposals for what we should call these models. K-scale, kilometer scale wasn't appealing. I have to report that on a car ride, Gretchen Mullendor, Kath Senior, and I have come up with a wonderful acronym. So there is competition. That's just to needle you all a bit. We have one and we love it. So if you don't put anything in, we'll win the prize. Andrew.
Yeah, I'm going shopping. We were discussing I'm going shopping this afternoon for prizes, so this is going to happen. Just the other thing to note, if you have the afternoon off, obviously there are many opportunities in Boulder. Just to note, there is actually an NCAR shuttle that we can get people to schedule from that will leave from right out here. That will take you across town. Some of them will go in towards town, to the main part of town. They also go to the different NCAR facilities. So that's an option for people if they wanted free transportation to get around. But just noting that.
Andrew, it's probably worth noting. It's probably worth noting that there's a number of mountain trails that begin at the Mesa Lab. So if you take the shuttle up there, there's lots of beautiful trails that take you into the forest and the hills. I've been here all week, but my wife has been hiking and tells me the sumac is changing beautiful red, and it's bright and lovely. And I think the aspens are past peak, but there aren't a lot of aspens right here in the Front Range. But the sumac are changing, and it's quite lovely. So if that's appealing to you, head to Mesa Lab and grab a trail.
And go early, there's a cold front coming. It's going to be here about 5 p.m. from what I understand.
There's a forecast. Call on it.
Oh, I saw it on TV, that's all.
Is that from the EC or from the GFS?
I don't know what they use. All right, so why don't we get started? So our first speaker today then is Richard Loft, and followed by Sherry, and they're doing a tag team. So they have asked to do 2 times 12 minutes and then only be asked questions at the end. So that's how we're going to do it. Richard, go ahead.
Okay, well, thank you very much. I'll try to live up to the opportunity to pretend to be Ollie Furrer in some ways. So today we're going, as was mentioned, Sherry and I are going to tag team a discussion about the computational science and software engineering aspects of the Earthworks project. On Tuesday, you may have heard Dave Randall talk about the science aspects as the PI of that project. And like a lot of these projects, you can see there is a lot of people who have been working on this, and so the list of people on this slide is quite long, as is the number of different entities and companies involved. My version of the Marvel Comics origin backstory for Earthworks is work that we did about 5 years ago in collaboration with IBM, the weather company, and NVIDIA, in which the weather company approached us to provide a GPU-enabled impasse. And serendipitously, we were already looking at trying to port impasse to GPUs on the, in a curiosity-driven way to see if directive offload could actually work reasonably well for a model. And so the objective was to produce an NWP forecasting system with about 30% of the planet refined to 3 kilometers. Essentially, the weather company wanted to have 3-kilometer resolution over the populated areas of the world, i.e. the land. And they also recognized with impasse that it had local mesh refinement baked in. So it took about 2 years to get impasse fully ported as a standalone meteorological model to GPUs. And when we were done, we were able to run on Summit. I have here about 4,200 GPUs. That's about 700 nodes of Summit at full resolution 3-kilometer. And we had to take some shortcuts, one of which was we didn't want to port the radiation because it was in progress elsewhere. So we adopted a lagged radiation where we used the heterogeneous node fully, using the CPUs to calculate radiation while the atmosphere was running on the rest of the dynamical core, and physics was running on the GPUs. This ended up going into production at the weather company in 2019, and we retained the code with OpenACC as open source. So just a couple of results from that exercise. The left shows weak scaling, so this is holding the amount of computation per computational element constant, and then scaling out the number, scaling the resolution proportionate to how many devices you use. And so these flat curves show that it weak scales. And then the strong scaling studies, the 3 orange, green, and brown show 10, 5, and 3 kilometers, and the blue is 10 kilometers, but run on NCAR's Cheyenne system. So we got acceleration, and this set family of parallel curves like this is a characteristic of going to higher resolution. And that's 1 year per day at that time on Summit. So for Earthworks, the premise in the proposal is, can we take this NWP success and translate it into an Earth system model? And the target was global, quasi-uniform resolution, put all the components on one mesh at the same resolution. That obviates the need to do interpolation or some kind of regridding that introduces potentially errors. Target these global storm resolving resolutions, focus here on the G11 icosahedral type grid with 41 million points. That's the kind of the target we settled on when the proposal was written in 2019. And the goal, you know, the moon landing type goal for us in the proposal was half a year per day at 3.75 kilometers. So one of the things that we have to do is sort of, you know, we're leveraging CESM, and we want to run CESM at high resolution, as does the SEMA team at NCAR and the CESM core team. So we've been looking with them at some high resolution results for Earth, an Earth system component that looks like atmosphere, land, and a data ocean. And this just kind of underscores what happens on a CPU-based system when you run on this. You see the atmosphere, the blue piece of this pie, dominates computational time. It's about 90% of the time. Long turnaround times for this is 512 nodes. It's about an eighth of our system. I say our because I worked at NCAR for 27 years, so their system, you know, an eighth of the system. So to get a run in requires draining a large chunk of the machine, so you can wait in the queue for a week to try and get a big run like this done. We actually, when we ran this, we revealed some issues with how the model scaled. This particular run spent as much time initializing the land surface as executing the model. That's been fixed, but you have to run at these scales in order to find these kind of problems. And then the slow throughput, the actual, when you're actually running here with the this test case, you run about 0.08 simulated years per day at 7.5 kilometers. So earthwork strategy, just using that as an example, you know, what we've done is use regional refinement of impasse to reduce the cost of tuning the climate parameterizations at meteorological length scales. So we're trying to avoid running fully refined models at ultra-high resolutions to tune that for cost reasons. Target heterogeneous computing with GPUs, that's kind of obviously the point here, but we need to accelerate things in order to get these GPUs can accelerate this code to something more reasonable than 0.08. Based on the times, in a fully coupled runs, you can focus on the atmosphere and the ocean. So our picture here shows GPU resident, atmosphere and ocean, and then everything else on the CPU part. So we're relying on the same trick that we used for the weather company, and that is keep things on the CPU that are a pain to port. So based on what I've heard here, the land surface may come back to bite us as something that we have to go back and port. But at the moment, the notion is to leave it on CPU. You can't really get much throughput if you need to use a large fraction of the computer. So we need to go after really big machines, exascale machines, as the target platforms for these things, so that we can actually get some turnaround time. And I think it's important to at least mention that our project also recognizes the huge data problem that is entailed by this kind of approach. So here's an example from microphysics being ported from CPU to GPU. Most of the, I'm doing this because most of the time you'll see the die core first and not the physics, and so I'm trying to turn that on its head. And there's a few, I won't go through the whole setup, it's here if you want to read it, but essentially this plot, the cool colors are CPU based results, Intel processors basically. And the warm colors are GPU-based results, either OpenMP or OpenACC offload. And you can see that the two types of CPUs and GPUs have very different characteristics, and they show up in the physics. The number of columns per node that's optimal for a CPU is essentially exactly opposite of a GPU. Now, in this setup, we just have embedded a GPU-based physics in with the CPU model. So you're actually not seeing all of the stuff that's going on with the GPU because of the data transfer back and forth. So we expect the data transfer to go away, so the actual GPU numbers are quite better than this because of that, including that overhead. And Sherry will talk about this. This is where the atmosphere die-core is, and you would think this would be the easy part, but MPAS 7 is quite a bit different than MPAS 6 because MPAS 7 is designed to go into the climate model, so there's some restructuring. But I think the key point here is we have some latency issues and some computational issues that we discovered in MPAS 7 that are associated with MPI weight and with some computations, some variables that we didn't capture as being GPU resident. And so we're working on this. But this advantage seems to persist in the newer architectures that have come out since the old result. And we think 10 kilometers, 4 simulated years per day on 256 A100s is a reasonable simulation rate. With the ocean, we've got 6 times faster than a Broadwell node on this system we tested on that's at NVIDIA. That equates to about 12 simulated years per day. We think that this is for a particular test case called EC 60 to 30. When we take that down to 3 kilometers, we think we can get multiple years per day out of the ocean with a very relatively small number of GPUs compared to the atmosphere. So we're in good shape, I think, with the ocean. And then with data, it's like, be careful what you wish for. The model could produce, we estimate with hourly output, 1.5 petabytes per simulated year. That's a lot, so we plan to use data compression, parallelism in the form of task, or Dask, I should say, the Dask Python library for workflow, and chunk it out as ZAR chunks. That allows us to use like S3 cloud type storage, and there is a netCDF ZAR. So there's a possibility here to have a chunked parallel compressed accelerated analysis package. But analysis packages just go on and on, so that's a major challenge. And the outstanding challenges, when you introduce GPUs, you take the model from a place where it's been designed and tested to a new place in the I/O subsystem, in the MPI system, and all of those things create issues. So for example, decoupling the number of ranks per GPU between ESM components, that's an issue. So internal to a component, like the die core running on a different number of MPI ranks than the physics. Intercomponent load balancing between GPU and CPU resident ESM components. The other thing I would say is just heterogeneity in these nodes is not going to decrease, it's going to increase. And so we have to become adept at mapping these models to heterogeneous architectures. Precision, it's been mentioned a couple times, but 32 bits is the new double precision. We have to figure out how to run some ESM components in 32 bits and how to structure that into the way we build models. And big data, I think even if we have a few analysis packages ported to be parallelized and compressed in all this, we have a lot of work to do to get all the analysis packages we want. And with that, I'm going to save the questions to the end and give this to Sherry.
Thanks, Rich. So I'll be talking about the software engineering challenges that we faced in this project. So basically talking about how we got the results that Rich just showed. Oops, wrong way, sorry. So I threw a whole bunch of stuff on a slide to show how complex this software development project really is. And I'm going to start off by pointing out the, let's see here, there it is. This first diagram up here in the right top-hand corner. So we are coupling MPAS sea ice with MPAS ocean within the CSM infrastructure, which presented a whole bunch of software engineering challenges in order to get that working. The other challenge we have is these models continue to develop. So they're not static, they're being developed orthogonally to our own project. So how do we actually coordinate porting code to GPU as the code is changing as we're trying to do our work? So we have that extra complexity as well. We also are coordinating this effort across many different organizations. So the project itself is led through Colorado State University, but we're also coordinating the effort between many labs here at NCAR. We have the private sector with help from NVIDIA and Rich's new LLC, R&D, as well as some efforts within the Department of Energy as well. We also have a very complex software stack that we're also trying to coordinate across many of these different systems that I show here. So how do we do this? So we form a good, strong community and have a very clear development plan. So, you know, when you think of software engineers, I'm going to throw this out here. We're stereotypically introverts. We like our offices. We don't like to coordinate. But in the efforts like this, we just can't do that. We have to coordinate. So an important part of this project is getting everybody in the same room, or Zoom conference call nowadays, and making sure that all voices are heard and that they're equally important in all these conversations. I personally like to celebrate all successes, so every little accomplishment we make, we celebrate as a team and keep everybody motivated and moving forward. It's also, as a group, important to create that clear vision and path, but everyone, a part of the project, should also understand how their contributions fit into this bigger picture. It's also very important to remove any barriers to entry, so new people can join the project very easily, but also, as you know, parts of the project struggle, we can go ahead and transfer team members back and forth to help each other across the project. But it's also important to empower all team members. So as the lead of the software engineering effort, I always try to find opportunities to create leadership roles for the team members. So they have a chance to grow their leadership skills, but also their technical skills as well. We also need to definitely coordinate our effort with the scientists. So, you know, from our experience, the scientists have to be equally invested into the project. We can't go ahead as software engineers and say, we know best, this is what you guys are going to do. They need to be invested into these projects as well. We also need to be aware of the science planning that's going into it, as well as the scientists need to be involved with where we're going software engineering wise. We need to be in constant communication with each other. So as a team, part of our team is embedded into the science meetings, and we also notify the scientists in separate meetings our planning from the engineering effort. It's also very, very, very important to have that exit strategy plan. So as we leave, as we complete these projects, how is this software going to be maintained after the work has been completed? And that's always been kind of a difficult, you know, funding, there's a whole bunch of complications with that, but that is definitely important because we don't want to create something that's going to be stagnant and not be able to move forward. So when we think about the software development, it's very important to have version control systems. So as a project, we've basically set up a repo that sits parallel to CSM. And we did that because even though all the changes we're making in regards to CAM and the GPU port are going right into CAM, we are also, remember, coupling MPAS CIs and MPAS Ocean into this infrastructure, which doesn't fit in the long-term plans of CSM. So we had to create a parallel repo for this work. And the way that this repo actually works is it actually just contains an external config file, which basically is a recipe of exactly all the repos and all the different repos and all the software stack within Earthworks, within CSM. It pulls it down and kind of contains that recipe. So it's really lightweight, but all the information is there. So as a project, going the GPU porting route, it's, we're like all other institutions. Which way do you go? We went the OpenACC route for most of our development, mainly because of the research that we have right now from this plot that Rich showed a similar plot earlier. We are seeing better performance with OpenACC right now, so we are going in that direction. But we are aware that OpenMP offload is still being developed, and so it's still on our radar. And we have a separate research project that's looking into, okay, we went OpenACC route. What if we have to switch to OpenMP offload? OpenMP offload has the advantage that we can run on Intel GPUs. So right now with OpenACC, we can run on NVIDIA GPUs, we can run on AMD GPUs, but we can't run on Intel GPUs. So as performance improves with OpenMP, or we're needing to run on Intel architectures, we've investigated this tool actually from Intel that I highly suggest if anybody else is in the same situation. We found that it gets you about 90% of the way there in performance as well as portability. So we've actually looked at it with some complex codes like CM1 that's developed here. It's a cloud model, as well as this Puma's MG3 work. I also wanted to give a shout out to Project Raysion, which Rich had a little bit of a blurb about it. But basically what this is going to enable us to do is to seamlessly analyze data on unstructured grids. Right now we're kind of in that situation where we have to regrid all of our data before we analyze it. This will provide that seamless transition to reading in the data and then automatically analyzing it within like Xarray DAS. So it will be able to exploit that parallelization within our workflow very easily with this work. So stay tuned for that. And it wouldn't be a computational talk without talking about testing infrastructure. So during development, for GPU work, it is very, very, very critical to test often and worry about performance later. It's very, very easy to lose correctness when you're doing GPU work. So it's very important to be testing this every iteration just to make sure that we as software engineers aren't changing answers for you guys. So the way we do this is, we've done this a couple different ways. So for the MG3 Puma's work, which I mentioned earlier, we actually used a tool called Cajun to develop a kernel. And what I mean by that is this tool goes into CAM code, for example, extracts a little test, captures the input and output, and we end up with a self-contained test that we're able to run. So we did that with the MG3 Puma's work just because it's not a standalone test. And we were able to iterate back and forth very quickly on the development and then put it back into the model. For the club work that we're just actually starting, club is very nice. It has its very own testing infrastructure, and it's a standalone application on its own. So in order to do this porting, what we actually implemented, actually we didn't, UW-Milwaukee did, Vince Larson and Gunther did this, where they added the multi-column capabilities. So we're going to go ahead and iterate back and forth on the development quite easily with this multi-column capability that they added. Now, after development, we have some CAM regression tests that have been added, so we can go ahead and move to a different part of the project, and the science can still keep going on, but they'll let us know if something breaks. So the way that they do that is they have two different tests. We call it a smoke test, where it just does a test, does it run? And we also have another bit-for-bit comparison test, which compares between CPU and GPU. So then we can tell if our answers are different. So what are we promising with this? So December of this year, we're hoping to get out more of our CPU capabilities and our configurations that we have. Starting next year in May, we're going to be releasing more of our GPU offload versions of these packages and a 15-kilometer resolution configuration. And then a year from now, we're going to be releasing more of our GPU offload capabilities, another resolution, but we're also going to be looking at releasing our diagnostics and our analysis packages. And then finally, hopefully, May 2024, that sounds way off, but it's going to happen quick. We're hoping to finally have our final configuration and our final data analysis package. So how are we doing? So when we look at our CPU route, we're doing fairly well. We're pretty much on target. As Rich says, the iteration process, as soon as we start getting the higher resolution, it takes, we can get one job through the queue a week. So it's really limiting our throughput in that regards, but we are making some good progress. And as Rich said, we're sitting at about 0.08 simulated years per day with the atmosphere land configuration at 7.5 kilometers. We're hoping to speed that up by about like 12 times. And then where are we with our GPU effort? So we're doing fairly well with that as well. So as Rich mentioned, we have already completed the dynamical core, the MPAS 7 version. We've also completed the port of Pumice as well. Right now, we're validating the radiation, the RRT MGP. We've hit a couple compiler issues with that one, but we're hoping to work that one out. We're currently working on the club port. We're just actually starting that, so we're hoping to get that done within the next year. And we're also evaluating the other physics within CAM itself to figure out exactly how much work it's going to be and where the slowdowns are and other parts of the package that need to be ported to GPUs. I think that was my last slide. So Rich and I can take questions.
As they were tag teaming, you can ask questions to either Richard or Sherry or both.
Hi, my name is Nikolai from Avi, so we're doing something similar. It was a great talk. My question is about your testing. You're developing code on GitHub, and you have to test it. Well, probably every pull request gets tested somewhere. Is it tested like on GitHub Actions, or basically my question is, how do you test your code on the HPCs? Because our admins basically freaked out when you asked them that you have to do unit testing on HPCs, and they say, no, it's never going to happen.
Well, thanks for the heads up, because we actually just put in a request for that.
Well, good luck with that.
There are system admins, so that's probably why we haven't heard anything back from them. Basically our testing right now is the regression tests that they do for CAM. So every single time they're getting ready to release or do another tag in CAM, that's when they run those particular tests. When we're actually testing during development, it's, for me in particular, I port, a module and I run the test and see if that's different. So unfortunately, we don't have any CI
So it's not
integration going on.
automatic, it's more right now
Unfortunately
hand.
not. Like I said, we have the email in. We'll see. I'll let you know how that goes too.
Yeah, that would be great to hear, because for us it's
Yes.
right now pretty hard.
Yeah, it would be nice. Yeah.
Yeah,
thank
can
you.
I just wanted to say that, two things about this. One, we have the added issue of not just testing at one center because we're targeting DOE exascale systems. So we've written essentially portability test request type small allocation request. When the testing gets to a certain size, they start to say, what's the, where's the science headline related to this? And I think that's where we run into an issue, because at some point it's too big to be testing and too testy to be science driven. Yeah, if I could, that's not the right word, but you know what I mean.
We're in the donut hole.
Well, there's some kind of donut hole like there. And I guess the second issue is part of the pull request is a lot of times has a code review, which is a manual process, and that takes up some time. So we can't always just trigger an automatic, build test kind of cycle because of that. So if changes have been made, we have to review them and stuff.
All right, you have quite a queue lined up here, so go right ahead, Gökhan.
Just a quick question. When Earthworks proposal was submitted, and you indicated too, there was a target simulation years per day. And it was like, I can't remember what the exact number was. Right, at 3.75 kilometer resolution. Now you're into like 2-3 years into the project. You know a lot more about the capabilities and all that stuff. Are you on target in a coupled system with 3.75 kilometer to accomplish that goal by May 2024? Or can you sort of say something?
I'll answer that one. Yeah, the results from the A100 and where we feel, I'm comfortable with the notion that we can hit that. There are some dependencies, like we have to get club ported, we have to get the radiation actually running on GPUs. One of the problems with the GPU thing from a projection point of view is it's an L-shaped ROI curve. So essentially you don't get any speed up until everything's ported, so there's no hosted device traffic between the different components. Once you get everything over, then you see this big benefit. So that's why I mean it's L-shaped. Managers like linear ROI, like I invested $1 million and I got this much improvement. And that's part of the scary part in making these projections. But right now, looking at the ocean and looking at the atmosphere, I think we might actually exceed that, especially with the progress that the GPUs are making right now in terms of the actual performance they're returning generation over generation.
Okay, thank you, Falco.
Thanks, Rich and Sherry. It was actually the best overview of Earthworks I've seen so far. My question is, are you planning to host any workshops similar to CESM workshops or WRF workshops? Or will it be as easy as running one of our standalone models? Eventually, once it's all done, can a grad student just go to GitHub, download it, or is it going to be more complicated and we need to bring people in and teach them how to do it?
I think, yeah. The PI's not here, and it's starting to feel like a PI question. But
Yeah, sure. If a grad student has an exascale machine, no problem. I mean, Earthworks is a configuration that's targeted at a specific thing that is the global 3.5 kilometer coupled. So it is supposed to be a comp set of CESM. So in that sense, yes, it will be possible, but the computational load is going to be excessive. There are going to be other versions of CESM using these components that will be easier, the regionally refined stuff, things like that. Again, there should be comp sets. It's going to be a community model. So it is going to be there, accessible, able to explore, but the computational resource for this is definitely, this is the exascale part. But it doesn't mean there are not other parts, if that answers your question.
And there is a plan to hold a workshop. I just don't remember the details of where it. Yeah, so we got a workshop. I think one thing is that you need that version 1 out there, even at low resolution, so people can kick the tires on it. And then you have an opportunity to have a workshop where people can test stuff after they go to the workshop.
Well, so that would have been my question. Are there any plans to run anything with the model? Or are there just plans to build it and prove that it could run if someone had a computer?
PI level question, we're just down in the engine room. Well, yes, and as part of it is you have to build a community. We don't want to just run experiments ourselves. We want to give it to the community and then have people get allocations on big machines and do the science that they want to do.
Yeah, but
so it's not sort of like we're building it for ourselves.
I'll let Mike go because we have a couple of minutes for two questions. So try and be brief, everybody.
I'll try to be brief. Thank you for your talk. It's very informative. I like that. You did make a comment about land, kind of like, oh dear, we have to deal with that. But given Martin Best's talk from Tuesday and looking at being on different resolutions or grids or whatever, how might you think that the land could be accommodated? Because whenever we look at Earth system components, it's ocean and sea ice and atmosphere. Oh yeah, land is always underneath there. So just curious about those future thoughts, and then thinking about what Martin said on Tuesday.
Well, it's exactly because of what Martin said about the land possibly getting much more expensive. And I also think that Tim Schneider mentioned that when they run sort of wharf hydro type experiments, the land consumes about 25% of the resources. Whereas when you look at the pie chart I showed at 7.5 kilometers for CESM, the land is, 5% or 6%. So if it grows, then the whole idea that we're just going to keep it on CPU and not deal with it stops working because you don't have enough CPU power to calculate the thing. So at some point, there's a sort of possible bifurcation point where you say, okay, the hell with it, I'm going to port it to GPUs. And that is, that's not factored into our current work plan, but it may have to be.
It's going to take a lot of work to actually do that, the way that the data structures and the loops are within that. So, I mean, it's probably better to start that conversation sooner rather than later, especially as these models go through all these, intense development efforts. We probably want to be part of those conversations now versus, hey, we really need to do this right now or yesterday. And, then it takes us even longer to get there.
By land, I meant, land hydrology.
So we let Tim comment on it.
I just wanted to clarify one point quickly. So that the 25%, Rich, I mentioned, it wasn't just land. That included full river hydrologic riding at a very fine scale. So it was more than land.
Okay, yeah, all that stuff, plants, birds, rivers, everything, whatever, all that 25, if it becomes bigger, then it can't be ignored. That's something I learned by raising children.
I'm a complete outsider, but I saw a version of the NCAR land model that had hill slope effects in the talks that were about Alaska. So you must have a version floating around where you can play and see what the consequences of making it more complicated might be. So it might be one of those where people don't talk to each other cases, but if there is stuff out there to try how much more expensive it might be. No, we don't have time for any further questions, I'm afraid. So thank you both.
Thank you.
Because we have an online speaker who's ready and raring to go. So our next presentation will be by Milan Klover, who is joining us from Oxford, I presume. There he is. And he will talk about data challenges when we go to these very high resolutions. And we can see your presentation now, Milan, and I will give you after 35 minutes, I'll shout into the microphone because that's the only way you're going to hear me. All right, so take it away. Thank you.
Perfect. Yeah, thanks everyone. Thanks for having me. Yes, I'm in Oxford right now, so I did not make the big trip over the Atlantic. But I do want to talk about different challenges around data. And while being at Oxford, yes, we collaborate with ECMWF, but so many of the things that I want to talk about are probably a bit more high level, a little bit less like technical implementation details. There's a lot of probably view from ECMWF spiced in, but also because I'm not directly working at ECMWF, I'm kind of approaching everything from a slightly more naive point of view. And I actually found it very helpful to stir up discussions and to question things, whether we should always do it in this way or that way. And I hope, therefore, you will also have a lot of discussions from me after this talk. So there's a lot of collaborators, people that I've talked to over the last years or so in order to understand the different perspectives around data challenges, especially when we produce a lot of data. And so the very first plot, I actually just put that together yesterday because I've received some data from ECMWF, how basically the archive scaled over the last decades. And I basically want to ask the question of whether we will actually enter the Google regime, meaning like how long does it take us to have as much data acquired as Google had a couple of years in their archives, which is well, just an estimate from XKCD, but you can basically see ECMWF's archives at the moment is, well, that was December last year, was at beyond half an exabyte. And if we project that forward, and this is literally, there's no more science than just literally hand-drawn a couple of exponential curves in there, then by 2030, 2040, we will be somewhere between several exabyte, and if we didn't do any compression and didn't do any cleanup, we would actually hit the zettabyte, which is obviously an enormous amount of data that I just can't imagine. But you can also see that there's a big scope for compression. So if we simply were relative to where we are now, have a tenfold compression, then we kind of like gain something on the order of like almost 10 years. If we had 100 times compression, then we would gain probably like almost 15 years or so in terms of this race towards the Google regime. And this is obviously, yeah, puts out a massive challenge and really motivates us to think better about how we store our data and how we make it accessible to our users. Because on the other hand, while our archives have been exploding, actually we have not thought that much about how we represent our data in a bitwise way. Because back in when ECMWF started their forecast, they used double precision floats. The IEEE standard was actually officially only introduced a couple of years later, and only last year ECMWF switched to single precision. So while we kind of went from these black and white graphs for weather forecasting, and now we talk about digital twins in terms of the numerical precision, not much has changed. And this numerical precision then also leads to the way how we store data in our archives. And while there was probably a bit more movement on the data compression side, I believe it's not as much as, did not receive as much focus as it probably should have received, given the problem that we'll be facing soon. So I kind of want to give a little overview of what different aspects of data compressions are out there, because I feel like in this community around high resolution modeling, data compression is always the thing that's like put at the back, like, yeah, maybe we'll deal with it at some point later. So I kind of want to raise a couple of issues around the things that are currently out there, that have been researched on, that have been developed. And I feel that data compression, you can often group it into two groups or two schools. And the first school is this, like, let's say, transformation school. So they're really the physical perspective, meaning you ask the question of, I have some data, what is the best basis function to represent this data? And so basically I just have some coefficients that I multiply with these basis function, and that represents my data really well. And the idea of that is obviously that you somehow approximate the spatial structure, spatial or even temporal structure, if you were to compress in time. And I mean, I just gave this example of like the spectral transform that you could think of representing data in terms of spectral coefficients. There's EOFs that people probably have heard of. You could just truncate them, and then basically you have some kind of data compression from that. But there's also more modern approaches which are for example, tensor trains and neural networks. All of them basically somehow include that, or most of them are fairly expensive to compute, because you have to do a lot of floating point operations in order to get into your transformed space, and also in order to get it back. because you basically represent your data with some kind of underlying basis function, it is often difficult to bound the error to know a priori what your error could be, because if your data does not really fit the basis function that you're using, it makes sense that kind of like you easily beyond some bounds, and it's quite difficult. For many of these approaches, actually also random access isn't really easy to do, because you basically say like you want to know what, I don't know, the temperature in New York is, and then for the spectral coefficients in like your spherical harmonics, for example, you would need to transform everything back in order to know one point. So that obviously makes the random access a bit tricky. The second school, and that was what I would like to highlight a little bit, is the kind of like the school around precision and information theory. I will talk a bit about this a bit more in detail later, but one of the underlying properties of that school is that you don't really think about the spatial structure in terms of like the physical perspective, but most of the time transforming it into this new encoding, whatever this encoding is relatively cheap. If you understand, for example, how floating point numbers work, or how like a linear quantization or logarithmic quantization works, your error bounds are also relatively rigid, and random access is also usually much easier because it's more straightforward how to chunk your data into pieces. And so you can easily say like, I just want to decompress this one chunk, and then here you go. This is definitely, so tensor trains, for example, back to the school of transformations, is not something that I've worked with, but I definitely would like to basically present it out there as like a thing that we should look out for in the future, because I think some of these approaches could be really promising. The tensor train approach is basically the idea that you just have lots of tensors that you multiply together in order to represent your n-dimensional array, which could obviously be like spatial, temporal dimensions, as well as like ensemble dimension, and so on and so forth. And at least the few papers that I've seen out there on these ones so far, they basically claim to be like really, really accurate at super high compression factors. So for example, this picture that I've plotted here on the left, that's super close to the original, at like compression factors above 3000. So absolutely unbelievable how this is possible to be achieved. But they're basically there to they're really good in representing smooth data. And just as a comparison, there's other techniques which also belong to this group of transformations that, for example, the ZFP splits your data into little blocks and then basically puts little basis function into these blocks. And that's why if you ramp up the compression a bit too hard, that's why you get these block structure appearing. And similar for SZ, which basically fits a couple of functions in there, and that's why you see these faces on the otherwise smooth surfaces that should be. So tensor trains, I think in general, are really good to keep in mind if you want to represent smooth data. It is not clear to me how they generalize to data that could be super sharp edges on one end of your field and rather smooth on the other one. I think they're more on the end of being fairly expensive. It is unclear to me how they generalize to, for example, unstructured grids, because obviously when you unravel your, let's say, two-dimensional field into a single dimension, and that I think that takes away basically a lot of compressibility for these methods, because they can't really exploit the neighborhood of your given grid cell. The next approach that I also haven't worked on, but I saw one or two papers on that recently, and so I want to put it out there because I think this is something that could be really promising for certain applications of data compression. Now, we'll talk about these use cases for data compression in a bit. Is this idea that you could also use a neural network to compress your data. And so the idea is really that you say, I have some kind of n-dimensional array that has some coordinates, X, Y, Z, time, ensemble, whatever dimensions you can think of. And you basically train a network to return you the scalar at a given coordinate, given the input coordinates. And so you basically start by defining an architecture for your neural network. You train it on it with some kind of loss function. For example, you say like, I want to minimize my, let's say, root mean square error. And in the end, you store the information of your original data set. You store that in the coefficients of the neural network. And so literally decoding it is simply just providing into this neural network your X, Y, Z, T, whatever coordinates, and it will basically do the inference then through the neural network, and you basically get out your one single point. The cool thing about this, and this is why I kind of like it, is that it basically interpolates automatically because it tries to fit a function through all your dimensions. And so it basically doesn't really matter where you evaluate that function, as long as you obviously your evaluation and training data set is coherent enough. You could just pick a point that wasn't actually where your that wasn't actually used to train your data and to train your neural network in the first place. But I guess it also comes with a lot of difficulties that I'm quite excited to understand in the coming years, because I think there's more and more people looking into this. But in general, it's a method that is rather expensive in terms of compressing things and decompressing things. But I've seen papers that basically claim, also factors above 1000x that should be possible. But it's really unclear to me how easily you can control the error and so on. So kind of want to put it out there, but I'm not so sure that's something that we would use directly. Basically going to the very other end of the spectrum, and this is kind of, for example, the standard that is currently used to eSIMWF using the GRIP data format, is this idea of linear quantization. I just want to quickly mention that. So for example, you go from you text your data set, you look for your minimum, you look for your maximum, and then you just split the range in between into equidistantly, and this is where the linear aspect comes in, equidistantly with some bits. So let's say you have 24 bits available, you choose the size for every number representation, and then you just split it into 2 to the power of 24 quants. And then these quants are basically, you then round your original data into these buckets, and these buckets then represent your data. The problem with that is that you really have to know what kind of data distribution you're actually using, because, and this is just like one of my favorite counterexamples, if you, for example, try to compress nitrogen dioxide with this, you will see a bit pattern histogram as it's shown here and at the bottom, that basically most of your values go into the very first buckets, and most of the other buckets are basically empty because your data is more logarithmically distributed rather than linearly distributed, so it doesn't really fit actually in there. And if you then look at things like the entropy, you see basically that 7 bits are effectively unused, and simply by all the values being in the first buckets and almost nothing in the other buckets, you can directly see that, for example, your first bit doesn't contain any information because you basically know it's going to be a 0, not the 1, which would then encode the second half of your range. An alternative to that is like logarithmic quantization, where you simply between the min and max, you then distribute your quants slightly differently, for example, in the log spacing. If you use the same data for that, actually, it turns out to be better because nitrogen dioxide is more logarithmically distributed. You can see that your first bit approximately is probably the information in your first bit is approximately 1, because it splits the histogram into more or less two equal parts. And so it's quite interesting that basically this is one of the challenges that we're also facing, that we basically need to know what our data looks like, what are the statistics of our data, in order to choose an appropriate compression method. And that's a big challenge. And I think this is definitely something that has to be worked on more to kind of automate this, to make it, to kind of develop standards of how different compression methods should be used. And I mean, this is probably where I would like to criticize eSIMWF, because at some point when they came up with their compression methods of using the linear quantization, they probably just thought about, that's the easiest way, and I absolutely agree it is, but we can probably do better by thinking a little bit more about what is the data that we actually want to compress, and what do we do with that data if we compress it in a certain way. And I think this is really highlights one of the more underlying things that we have to understand when it comes to data compression, is that depending on the method that we're using, there's different control knobs. So different things we can choose in order to make this compression method work better or not so good. And the first one, and this is basically in this linear quantization or logarithmic quantization, is really the idea that you choose the number of bits. So mainly you choose the size of your data set a priori, and then at the end, you get some error out of this in order to get to your compressed data. And this might be rather unsatisfying, because you kind of need to work your way back in order to understand what error actually happened in your data set given a certain size. But you might be, let's say, like positively surprised if it's really small, but you rather would like to control the error rather than the size. And so let's say the second group of compression methods, and many of the transformations fall into that, is that you basically choose your maximum error that you're happy to tolerate. And often this is literally just like one scalar that you choose. So for example, for this ZFP library that I've mentioned earlier, that splits everything into these little blocks, you kind of say like, yeah, I want to have a maximum absolute error of X, and then press play, and then it kind of compresses that. And at the end, you're like, my data set is that small. So you really go from this error to the size, and then you have your compressed data. However, all of these, all of these methods that fall into group 1 and 2 are basically such that the compression step and the information loss step are combined. So you can't really disentangle them, which, and this is why I've mentioned group number 3, might be, especially in our applications where we do, let's say a lot of research around it. So meaning you want to like swap out different parts and kind of play around with things and understand how they work and which parts could be done better, is that actually there are methods that let you choose the errors independently and really literally for every number. And we'll give one example later. And you can combine it with basically any lossless compressor that you can think of. And so you kind of take these 2 steps of like introducing an error because you've somehow truncated your system, your data, and choosing the actual compression step to make this independent. And this kind of, I think, gives us a lot of flexibility because we have a much better control about the error, as well as we can even later say like, we still want to keep the same error, but we want to have another compressor, which we know then, for example, is not going to affect our errors, which probably makes all the scientists going to work with that data happy because they know we still get the same errors before, but maybe it's like smaller or decompresses faster or slower and so on and so forth. And so I think it really makes sense in order to phrase this challenge a bit better is that we kind of need to see which use cases do we usually have for data compression. And so I kind of like try to came up with a couple of examples in order to highlight how data compression can be different, especially at really high resolution where obviously we have a lot of data to deal with. So case number 1, and then just like as an example, is like the typical case of reanalysis data. So meaning you have like one institution, for example, has produced a data set. It's a certain data set that is, it's like one data set, but it's basically used by many, many different people, let's say ERA 5 or something like this. So it's a data set where if it was small, it would be really beneficial because you could easily like download it to different servers, to different institutional clusters, and people could reuse it quickly. Because it is basically a data set that is compressed once, but decompressed many, many, many times by different users, decompression speed is basically really the key, but less relevant might be the compression speed, because you may say like, we actually would be happy to sacrifice, like basically have like a slower compression speed for a much smaller file size. And then also something like portability is obviously important because it's going to be used by different people. And they may say like, I just want to have like one grid location, but give me all the time steps, meaning you kind of have a random access of that data. The case number 2 is kind of like what I phrased here as like research simulation. So basically meaning like, I want to work on this project. I want to do this little experiment with my model. You run it and you basically, important is the compression speed because you may read it out many, many times. You also don't want to really include much of an overhead if you write to the data. You want to do like a random access, but maybe size is not that relevant because you're only going to keep it for a couple of months on your computer, and then you're going to put it into some long storage archive. Which is then case number 3, I think, where like really size is the absolute thing that matters. And portability may not be that relevant because it might be just a file that really is just stored there and isn't actually meant to be touched that often anyway. And so decompression speed may be not that relevant, random access may not be that relevant either. And then let's say case number 4, operational. Really, I probably couldn't think of anything better where like, let's say literally everything is important because you produce a lot of data, you want to distribute it to a lot of people, they want to access this on a frequent basis and so on and so forth. And so really the question that we should ask is, what do we compress, right? Because this is, I think, really the difference between these idealized cases that you see in a lot of different compression algorithms. Everything looks nice and smooth, and you're like, yay, we can compress that to like a factor of 3,000. It's like, yeah, but our data doesn't look as much as like a textbook example as your paper claims to be. And this is one of the examples that I produced by just looking at the different variables that are in the Copernicus Atmospheric Monitoring Service. This is one of the services that are operationally produced at ECMWF. It's basically the chemistry forecast of the atmosphere. And so you see here, basically try to put as many histograms into one plot as possible. You can see some of them are absolute, like, because it's a log scale, absolute spikes. So they're actually, their range is really small and they're more like linear distributed. Other variables span many, many, many orders of magnitude. It's a super multimodal distribution. Some value, they all have like varying uncertainties. Some have possibly like many, many zeros. If you think about precipitation, there's many areas in the world where it currently doesn't rain. Then also the problems that we're also facing are really that sometimes some fields are super smooth, some are really have strong gradients that may change with you from location to location, from vertical layer to vertical layer. Sometimes we store things on unstructured grid, or even sometimes we want to store things in spectral coefficients and have mask data and so on. And so for these kind of data that we're dealing with, the challenge to find a really good compressor is not bigger. And so I really want to ask this more underlying question in order to lead over to the topic that I actually want to talk about is this question of like, what information is there actually in a given data set? And there is definitely, in terms of, when you think in terms of dimension, in terms of information, there's definitely different dimensions, right? So we're here at a kilometer scale workshop, so meaning resolution is absolutely important for us. And the higher resolution, the more data we will produce, the more information is there in that data. But we also look at many different numbers of variables, and all of them come with numbers that can have some kind of precision. And so if we think about data compression, we kind of truncate this information space somewhere, and that literally made a little bend around the resolution, because Andrew Gettleman said many times now that we do not want to question the usefulness of kilometer scale. So definitely including the resolution, because I do not want to truncate any of that. But we may truncate something in terms of precision. And I think this is really where we would like to define this, let's say, what I call the real information problem of lossy data compression, is where you say, I have an original data set. I may have some research questions that I would like to ask, and I want to know what is the smallest subset of this data set, which can still answer that exactly that same question in a qualitative way. So obviously you do not necessarily talk about the bit reproducibility, but you basically want to have qualitative the same answer. So for example, your hurricane is still going to make the landfall at the same time, roughly at the same time. And so the question really is like, what, if we think about in terms of compression, what compression error is okay to have? And I just literally pulled a number out of a hat and said 303.25 times some unit plus some uncertainty. And the question really is like, depending on the application, on the use case, there might be certain digits in there that we trust and other ones that we do not trust and we would rather would throw away in order to save memory. And so if you think about this in terms of, let's say, Kelvin, because it's some temperature, 303.25 Kelvin, and your use case is a weather forecast that you want to communicate to users on their phone, then you may say like, okay, 303 is good enough. But obviously, if you think about something else, then maybe you want to preserve the 0.3. And maybe if it's about, I don't know, millimeters of rain over a certain period, you say like, wow, it's an extreme weather event. So our model is probably not good enough to represent that anyway. So we could just truncate it to 300, and it's basically good enough because it would be the uncertainty of that forecast is masking that that precision anyway. And so really this notion of like what is an acceptable error depends on a lot of different things that I've just mentioned. And so the underlying question that we want to ask is there any way that the uncertainty in our data can be estimated if unknown? Because for many of our variables, or like, let's say the other way around, for some of our variables, I'm pretty sure that people have a good idea of what the uncertainty is. Let's say temperature. But there's a lot of variables where we don't know. Is it like 10 to the minus 5? Is it 10 to the minus 3? Or is it something else? Do we really care about the relative or about the absolute error? So some people that I've talked to over the last years definitely said like, oh yeah, I'm happy with 10 to the minus 3. It's like, yeah, but how do you know? How do you justify that? And this is kind of what we wanted to tackle, find a framework that answers that question a priori given some data. And in order to motivate that a bit more, imagine you have some data here. And now it's just represented in some numbers, 0.05, and then you have some digits at the end. The question is, do you trust the digits at the end or not? Probably not. If you don't trust them for compressibility reasons, you should throw them away. And in terms of if you encode this into bits, the question therefore is basically, where do you put the line to distinguish between the stuff that's real that you would like to keep and the stuff that you would rather throw away, because these are the high entropy bits that are really not well compressible. So ideally, you do want to cut them off in order to get smaller file size, which, by the way, also means that you can directly communicate your uncertainty within the data set without encoding explicitly the uncertainty, which I find is a great opportunity of that. And so the question is like, yeah, do you just cut it somewhere, and how could you do that? And the idea for us was that we basically just calculate the information across bit dimensions, bit location. So basically here in the vertical, we kind of compare all the bits that are sitting in the vertical. So you may end up with like a bit stream of bits that are in adjacent grid points. And so just as an example here, in this bit stream, you would have zeros mostly followed by 0, and words 1 either remains 1 or switches back to 0. And so you can basically put this into a joint probability matrix. This is just an example here. For example, put into probabilities of transitions between 0 and 1, 1, 0, 0, 1, and 1, 1. And then you can calculate the mutual information. So basically the question of like, what does one bit tell me about the next? And is there any information in that? If there's no information, it basically suggests us that we should throw this away. And so we came up with this bitwise real information content framework that we hope is going to be helpful in order to address this more umbrella question in the future, which is, imagine you start with some gridded data. It doesn't have to be, it can be even unstructured, and you kind of like have some kind of space filling curve that basically moves along as long as your next grid point is somewhere adjacent in space. And then for every bit position, so let's say the sign bit, the exponent bits, the mantissa bits, you look at the bits that are in the surrounding grid points. If they're all identical, then your entropy is 0 anyway, so information also has to be 0, because entropy is kind of the upper bound of your information. But the mutual information, for example, if a lot of zeros are next to each other and a lot of ones are next to each other, your mutual information is actually approaching 1 bit. And so you can basically do that for every single position, and then in the end you come up with one of these graphs, as you can see in the bottom, which maximizes at 1 bit. That is basically the maximum information that you can have for a given bit position in your data. And then, for example, you see like that there's a lot of false information towards the end, and your real information is usually somewhere in the exponent in the mantissa bits, and then somehow tails off. Usually, I mean, because obviously this method does not know anything about your encoding, so you can actually apply it to a lot of different encodings as you want. And depending on what your data looks like, this might look a bit different, but most of the data that I've looked at is qualitatively something like this. And so the question that you can ask is then, how many bits do I actually have to retain in order to preserve a certain amount of information? And here in this example, for example, we say like the purple dashed line is the line that we would cut if we wanted to preserve 99% of real information in our data set and remove then the rest for compressibility. And so we applied this
about
to
5 minutes, Milan, about 5 minutes?
Yeah, that's fine.
Milan, if you can still hear us, we lost you, so you probably have to go out and come back in.
He's back.
I think my internet.
Milan, I'm going to turn off your video
sorry,
to conserve bandwidth.
Yeah, that's fine. I'll just show a few more slides and then we can go over to the questions if that's okay for you. Yeah? Thumbs up?
Yeah, no
All
problem.
good? Perfect, great. And so basically the idea is then that instead of thinking about error norms, I kind of motivate people to think in terms of preserved information, because this is actually a quantity that kind of moves with the statistics of your data better. And is hopefully, and we have to see whether we actually understand this metric in its full breadth, is hopefully a metric that is actually, it's a more useful metric for data that you don't know much about. And so in this example, we just compressed, for example, water vapor, and 99% of information. Compressing that gives us a compression factor of 40 roughly compared to double precision. Whereas then obviously if we were to go all the way to the right, throwing away about 20% of the information, we would actually get visual artifacts. So we're kind of well away from that. And kind of want to skip that. But you can also, in terms of high resolution modeling, we've also applied this technique to some satellite data. For example, here's brightness temperature, and it worked rather well. However, and this is probably one of where we get into the bad and the ugly aspect of this workshop, is that every time you calculate this bitwise information content, you end up in a situation where you get basically an average for your entire domain that you look at. So meaning here, for example, you would get an average information for, as well as these like patchy cloud features you can see, as well as, for example, the more sea surface temperature signal that you can see here over the Black Sea. And so this is obviously poses a problem. And we realized, especially when you look at fields, for example, like precipitation, which can be quite patchy in the tropics, but then rather smooth in, or more smooth in, at this resolution, at least in mid latitudes. And if you then calculate the bitwise information content of that, you get one number to suggest you should keep that precision. But actually, in the end, that might be more inflicted by the tropics. You may end up cutting more precision off in the extra tropics that you actually want to. A similar problem that we faced was that some people, for example, used floating top numbers, truncated them, expected an absolute error that was uniform, but realized no, it actually isn't, because floating point numbers are rather logarithmically encoded. And so the little transitions in the amplification of the error that you can see here are exactly the 8, 4, 8, 16 degree, 32 degrees isotherms. And so also one of the problems, if you think about this quantization, that happens then is that you basically filter out gradients that may cause problems here or there. I don't know, but it's basically, yeah, just saying that you kind of like neighboring grid points that you really can't significantly distinguish, that you basically put them onto the same level. Kind of want to skip that. And basically, in the end, we just want to say that we've been working on different implementations. So I've been writing this package called bitinformation.jl, which is my Julia reference implementations, and other people have taken it up, developing Python, Xarray, NetCDF, grep, HDF interfaces. So this is basically all something that we're working on to understand how it can be used, how it can be useful for people. And I hope, it triggers some discussion around how we actually store our data. And at this point, I think I would like to end this talk, and I'm very excited to hear any of your thoughts. Thanks.
Thank you very much, Milan. Questions? Yep, come up to the microphones, because otherwise Milan won't be able to hear you.
Hi, Milan. Peter Lauritsen here from NCAR. A couple of comments. To make use of data compression, I think there's a lot we can do on the actual model side as well. So for example, if you look at budgets in the model, they're very sensitive to any kind of truncation. So if, for example, what I talked about yesterday, those energy tendencies, I'm subtracting two huge numbers to get something order 1 out. However, if I compute those inline in the model, then it doesn't matter if you start compressing the data. So I just want to shout out that I think it's really important we compute a lot inline in the model, and then we can really make use of data compression. And you can make similar arguments for functionally related quantities in the atmosphere, such as chemical species. And then the other comment I have is, if you're a dynamicist, there are some diagnostics that require zonal means. So if you compute those after the fact, you need really high-resolution 3D data. And one issue with moving to these unstructured grid models is it's not trivial to do zonal means. That's, for example, something we're working on at NCAR, so that you can compute these kinds of eddy statistics in line, and again, in that way, massively reduce the amount of output, and then you could do compression on it afterwards.
Yeah, maybe just to respond to that quickly, I absolutely agree. And this is why I've been almost like advocating a bit more to do the compression directly within the floating point format, simply because it is a format that we do understand relatively well, where people have been putting a lot of thought into how to actually design rounding modes so that they're bias free, meaning that actually if we truncate in the floating point format, you should, at least theoretically, you should be able to, do not distort any budgets that you're calculating, which in the end, it's just like a sum over a lot of truncated values. But I do agree, this is absolutely something that we should also look out for, let's say, these like more transformation-based algorithms, is that it might be really tricky with them to guarantee that any kind of means, averages, and so on are preserved. And this is not a priori clear for those ones. Whereas for as long as you have like a bias-free rounding mode, this should all basically tick the boxes.
Yeah, thanks. I forgot to mention, great talk. It was really interesting.
Thanks.
All right, Andrew is next.
Hi, Milan. It's Andrew Gettleman. Thanks for your participation today, starting earlier this morning, our time, afternoon, your time. Again, great talk. I had a sort of general comment and thought that thinking about the concept that we have of stupidly parallel processing, maybe there's a form of stupid compression where we just don't output stuff. And this is kind of along the lines of what Peter was saying, that we think ahead about what we're going to use from these simulations, that we get out of a CMIP model of, at NCAR, we actually call these MOAR runs, mother of all runs, where we output everything. But maybe that's not the model we should think about. We should think about only outputting what we need to output based on the analysis. It's almost like thinking of the information content one step further through the analysis of, do you need it at all? And some of this, again, is what Peter was saying about doing things online, but I'm wondering if you had comments on that, and if there's ways of taking this information content even further upstream.
Yeah, no, absolutely. This is where kind of like my little graph came in, where I tried to like make the little bend around the resolution, because I think this is really what we actually in the end have to tackle, is that our information space is really high dimensional, including like what applications we use, who is the end user in the end. And I do agree, if we have a clearly defined objective that our data is supposed to do, for example, give us the temperature forecast at a given location, then it is relatively clear what we want from the data compression. However, and this is probably the caveat I want to mention, is that we all somehow work in research, right? So there might be someone coming up with a research question a few years down the line and say, like, I want to look at this. And suddenly this is an application which requires something different from the data. And I think this is the underlying problem that we are facing with all this data compression. That's why everyone's basically careful. Everyone tries to like, oh, no, I don't want to throw this data away because I may use it at some point down the line. And so, yeah, this is really where we have to find some kind of common sense. This is what we want to keep using, and this is not what we want to have, because no one's going to use it in the end anyway.
I guess one example that we always do, which is the first thing, is we do, we usually compress with resolution, but remember we have to think about resolution in 4D, and it's resolution in time, and then we lose information. But that's a convenient, way for us to do it. And we can probably think about that with respect to high resolution as well. What times should we compress, or what times do we just throw out? So anyway, just a thought.
Thanks, Andrew. Christian, Jacob here, I have a question too. So you mentioned, you had your precipitation example, which I really liked, where you saw the exotropics behaves different from the tropics, and then you compress it as if it was a global field. I mean, in principle, we don't have to do this. The one advantage we have is we know the system that we're modeling. So if we know the tropics noisy and the exotropics is smooth, why don't we chunk it and store the tropics in a different file than the exotropics? I see no a priori reason, other than convenience and tradition, why we wouldn't do that. What's your thought on that?
I have a better solution. And this is exactly this method that I frame as like round plus lossless, where you literally split the truncation and the extra compression to two different steps. Meaning that really the first thing you do is you basically just round the bits that you do not want to have, you round them to 0. And the idea there is that you literally you can take an array and you can treat the exotropics different to the tropics, but in the end it's still an array that just has more zeros in the tropics than it has in the exotropics, but otherwise it's not treated any differently. So it is suddenly a method that can have a variable precision in different parts of the array. And I think this is nothing that any of the other transformation-based approaches actually provide. But you can really, and this is probably where in the example, I kind of had these little error bars that were like different for different parts. It gives you an enormous flexibility in the precision that you want to preserve, because you can have a variable precision inside your data set. And the only thing you have to do then is you bang a lossless compression algorithm on top of it, and it will basically take care of the extra compression. So the user itself will never actually realize, unless they look at the bitwise data, will never actually realize that the tropics are dealt differently to the exotropics.
Yeah, but there may be other advantages in chunking in space, right? A lot of research questions concern the tropics. So many people download global fields and throw away 70% of them straight away because they're looking at a certain aspect. So I'm just saying there may be opportunities to be smart. So last question, though, goes to Pierluigi, and then we'll move on.
Hi, Milan. Just following on this idea of future uses of the data, I think you hinted at it in your presentation. There are also mathematical considerations. So we may want to take first, second derivatives. It's not just what we want to do with the data, it's what operators we want to apply to the data. Is there a way to take that into account?
Yeah, this is basically where all the transformation data compression methods that I've outlined a little bit claim that they're better at, because, I mean, in the end, they're basically fitting some kind of basis function to your data. And as long as that basis function is nicely differentiable, you basically end up also with a compressed data set that doesn't, once you compute, let's say, the gradients, it doesn't really get much distorted. I do see these advantages, and I find it tricky at the moment to really see, like, I'm still looking for applications where like someone calculates some gradients or something and it absolutely goes wrong if you use, for example, this like round plus lossless method. So if you have a good application, please just say like, oh yeah, for example, look at this data set, and if you compute the gradient of that, then you compress it, and then you want to look at this. Please share with me. I do see that it is absolutely a use case that's necessary for us, but I don't necessarily see yet that the transformation-based methods are make it basically like the gradient preservation of them make it absolutely worth considering them over the other class of compression techniques.
Thanks for the talk too.
Thank you again, Milan, for the great talk. You can see from the reactions everybody liked it. So we let Milan go and have dinner, I suppose, go home and have dinner, and we'll go and have our morning coffee break. And just to reiterate, there will be no more talks today. So after the coffee break, please go into your breakout groups and self-organize, but there will be lunch at 12:30. All right? Thanks, everybody.
Thanks, everyone. Take care.
Thank you, Milan, and we'll see each other in this room again tomorrow morning at 9.